In this section, we're going to be looking at entropy on the molecular level. We're going to be thinking about entropy in terms of the actual molecules themselves. And when we do that, we don't get a different result. The same things that we said were true earlier about things that increase entropy also increase entropy. It's just it's sort of a different way of getting there. So if we look at who got this all going, it's a scientist named Boltzmann, who came up with an equation to describe entropy, and he used statistical thermodynamics to do this. The equation he came up with we call the Boltzmann equation, which is this. The entropy S is equal to K. That K is the Boltzmann constant, and there is the value of the Boltzmann constant, times the natural log of W. And W is the number of microstates. And we'll talk about what a microstate is here in just a moment, but I'm going to tell you that a microstate, or the number of microstates, is a very, very large number. It's like large and then raised to another large number. It's ridiculously large in order for this quantity to have any meaning. So the number of microstates it's a very big number. So what we want to do is to look at that. Before we go any further, though, I do want you to get an understanding of what that Boltzmann constant is. It looks like something that's very different, but it's something that you've seen, but it's just sort of on a different scale. If you take Boltzmann's constant and multiply it by Avogadro's number, go ahead, get your calculator out and punch this in. I'll wait. All right, now that you have done that, now that you've punched that number in, you're going to get this value. Now, of course, that's a lot of significant figures, but it turns out that is an exact value, which is why I put them all. But normally, we only use the first 3 or 4 or sometimes even 5 of these digits. I usually just use 4 at 8.314 joules per mole Kelvin. And that, of course, is the gas constant. So that is the gas constant. The gas constant is essentially just Boltzmann's constant multiplied by Avogadro's number. In other words, the gas constant and the Boltzmann constant are closely related. They're essentially the same thing, except one is talking about the molar level and one is talking about the molecular level. All right. Let's go back to that equation, though. We want to talk about the number of microstates. Well, let's take the overall equation, and we're going to, we know that this is true, that we can calculate the change in entropy using this formula. And the reason we can do that is because entropy is a state function. State functions, we just have to know where did it start, where did it end, and what is the difference between the two values. And that gives us the value of the change. Well, if we replace, so S final minus S initial, we'll get K times the natural log of W final minus K times the natural log of W initial. We can factor the K out, and then we can combine the natural log of W final and W initial into one term that looks like this. And that will tell you what the change in entropy will be for your system. So if you know the number of microstates initially and the number of microstates final, then you can determine what delta S is. Now, I say that in reality, calculating the number of microstates is a nearly impossible task because the numbers are just too big. But we can conceptually think about what kinds of things will increase the number of microstates. Because if the number of microstates W final is greater than W initial, W final over W initial, if that's a bigger number, that means that number is bigger than 1, and the natural log of a number bigger than 1 will be positive. If W final, on the other hand, was smaller than W initial, somehow we decrease the number of microstates in our system, then natural log of W final over W initial would be negative. And that can happen for the system. I'll explain how it can happen a little bit later, but it can happen for our system. But here's the important thing. Anything that increases the number of microstates will increase the entropy. That's it. So anything that increases the number of microstates will increase the entropy. So it would really help if we knew how do we increase the number of microstates and maybe what the heck is a microstate. So that's what we're going to do next, is to analyze what a microstate is. So what is a microstate and how do we go about increasing it? Well, a microstate is a single possible arrangement of the positions and energies of the particles that make up a system. So that is what a microstate is. If you look at all the different ways that you can arrange the particles in a system and all the different ways that you can distribute energy to those particles in the system, the available energy, each of those ways is a microstate. The number of microstates is the total number of ways that we can arrange the particles and distribute the energy amongst the particles in a system. This is why the value W is such a large quantity. The number of microstates is going to be an almost uncountable quantity. All right? And again, it's mostly useful to think about this in terms of qualitatively, what can we do to increase the number of microstates? Well, if we increase the volume of a system, then there will be more ways that we can arrange the particles in that system. If we increase the temperature of a system, that means there's more energy in the system. And with more energy, there's more ways to distribute that energy amongst all the particles of the system. So, we talked about these two quantities earlier, or these two things earlier. If we increase volume, we increase entropy. And if we increase temperature, we increase entropy. Well, this is why. When we increase volume, we'll increase the number of microstates. And when we increase the temperature, we will also increase the number of microstates. So let's look at how it is that we can store energy in molecules. What are the different ways that we can store energy in a molecule? Well, we're talking about kinetic energy. How can we store kinetic energy in a molecule? Well, one way, we need to look at the different ways that molecules move. And one way that they move is called translational motion, and this is where molecules just are moving in a straight line and eventually will bump into something else. But it's movement of the entire molecule from one place to another. Well, we can put energy into a molecule that way. We can look at the vibrational energies. And down here on the bottom of the page, I've got a little cartoon here with the water molecules. And there are different vibrational modes for water molecules. So one vibrational mode is where both of the oxygen-hydrogen bonds are stretching at the same time. We call this one a stretching symmetric stretching. And so when it stretches, it's like a spring, and so the atoms will bounce back and forth. And when you have something that is a spring like that, you can store energy in it in that vibrating motion. You can also store energy by having the bonds actually bend, and we call this a bending motion. We also have what's called asymmetric stretching, so that's just another way we can do this. And, for water, that's all the possibilities, but for other molecules, there may be more possibilities and therefore more microstates. We also have rotational energy, and so we could store energy in a molecule by having it rotate. So we'll find that those are different ways that we can have energy in a molecule. And so the more ways there are to put energy into the molecule, the more microstates we will have. We'll also see that more atoms will mean more microstates, so more possible modes of motion. So water is a pretty simple molecule. If we had more bonds, then we would have more microstates. So let's take a quick review of the things that will increase the number of microstates. So if we've got something and we want to increase the number of microstates of that system, then we can increase the temperature. That will increase the number of microstates and therefore increase entropy. We can increase the volume, and that will definitely increase the entropy. And we can increase the number of independently moving molecules in our system, and that will increase the entropy as well. As far as physical states and the entropy of the different states, well, if we increase entropy will increase with the freedom of motion of the molecules. So the more that the molecule can move around, the more ways that we can store energy in that molecule. And so we will see that the entropy of a gas is going to be greater than the entropy of a liquid, which will be greater than the entropy of a solid. If you think about water, for example, if water is in the solid form, it's in ice, the molecules are pretty restricted in how they can move. You really only have vibrational modes of motion. The molecules aren't free to rotate, and the molecules are not free to move translationally. They can vibrate a little bit, but we're just going to have vibrational modes. We're not going to have translational, and we're not going to have rotational. If we melt the ice and convert it into liquid water, we'll see that there's more translational motion, increased freedom of translational motion, and increased vibrational and rotational motion. So that increases the number of microstates significantly. Once we convert that liquid into the gas phase, we will very dramatically increase the entropy because the number of microstates is going to go way, way up. There's complete freedom of translational, vibrational, and rotational motion. So this will have the largest number of microstates. So gases have more entropy than liquids, which have more entropy than solids. If we have changes in states, we'll find in general entropy will increase when gases are formed from either a liquid or a solid. Or if a liquid or solution is formed from a solid, that will increase the entropy. So here we've got solid sodium chloride, and then we've got sodium ions that are in solution. Well, when the particles are in the solid phase, they can't move around very much, so there's not many ways that you can store energy in that system. But once they are once they are dissolved, they can move around with quite a bit of freedom. So they have a lot of ways to move around, and therefore will have more microstates. If we increase the number of gas molecules, that will also increase the entropy. Over here, I've got a chemical equation, I've got a diagram that represents a chemical equation. We have 2NO plus O2 gives us 2NO2. So this is a chemical reaction that can occur. And on this one, actually, you'll find instead of increasing the entropy of our system, it decreases the entropy of our system. If we look at the total number of moles on the left side of the equation, we have 2 plus 1, so 3 moles of gas on the left side of the equation, and we have 2 moles of gas on the right side of the equation. Since we're decreasing the number of moles of gas, the entropy of that system will be decreasing. If, on the other hand, we were increasing the number of moles of gas, we would be increasing the entropy. And then, in general, if you increase the number of moles in a chemical process or chemical reaction, you will increase the entropy. So let's go to number 32 on the in-class assignment. And what I'm going to recommend for number 32, I'm going to switch over. What I'm going to recommend for number 32 is to do what I did previously. I'm going to recommend that you try these on your own. Now, if you get stuck, play the video and watch as I do a few of them, but try to do these on your own. So stop the video and try to do them on your own. All right, I'm assuming that you just stopped the video and you have tried them on your own. So we want to say, how does the entropy of this system change for each of the following situations? In other words, does it increase or decrease? Some of these will be quite obvious and others will be less so. Here, the temperature of a system increases. Well, If the temperature increases, the entropy will increase. So I'm going to write increase there. The volume of a system decreases. Well, if volume decreases, the entropy should decrease as well. So decreases. Or I'll just put decrease. A liquid is converted into a solid. Well, going from liquid to solid will decrease the number of microstates, so we will decrease the entropy. So we'll put decrease. A solid melts. Well, there we're going from the solid phase into the liquid phase. So there we should have an increase in the entropy. A solid sublimates to form a gas. Well, there again, we're going from something with low entropy to something with high entropy. So we should get an increase in entropy. Equal volumes of ethanol and water are mixed to form a solution. In this case, when we put the molecules together, they will disperse. There will be more ways to arrange those molecules, and with more ways to arrange the molecules, that means more microstates, and that means an increase in the entropy. Generally speaking, when we mix things together, entropy will increase pretty substantially. A gas liquefies. So here we're going from gas to liquid phase. That's going to be a decrease in the entropy. A solid dissolves in a liquid. So when a solid dissolves and gives us a liquid or a solution, we will find that that will increase the entropy. An ounce of water freezes to become an ounce of ice. And so there we're going from liquid to solid phase. That is going to be a decrease. All right, so hopefully you're starting to get an intuition about what kinds of things will increase the entropy and what kinds of things will decrease the entropy. So let's go back to the presentation, and we're going to look at the third law of thermodynamics. And if you're wondering how many laws of thermodynamics there are 3 laws, and this is the third one. The first one, just as a reminder, was the law of conservation of energy. Energy is not created or destroyed. The second law basically told us that the entropy of the universe is increasing for spontaneous processes. And so the entropy of the universe is always going to increase. It'll never decrease. Well, the third law of thermodynamics tells us that the entropy of a pure crystalline substance at absolute zero is 0. So in other words, if the temperature is 0, then the entropy will be 0, provided that it is a pure substance. Well, in a pure crystalline substance at absolute zero means that there is no energy in that system. And with no energy, there's only one way to distribute no energy, right? And so that means that the number of microstates when there is no energy is going to be 1. So if W is equal to 1, then the natural log of 1, of course, is 0, and so that will give us an entropy of 0. Now, it turns out it is quite challenging to get all the way down. It's quite challenging to get all the way down to absolute 0. We'll find that any substance that has a temperature above absolute 0 will have some entropy. And that's the basis for our next topic, which is talking about standard molar entropy. So let's look at how does the entropy change as we increase the temperature. We know that entropy increases as we increase temperature of a substance because that's been one of the very first things that I told you guys about this. So the third law says that the entropy at 0 will be 0. So at 0 Kelvin, our substance will not have any entropy. As we increase the energy, there will be more ways to distribute that energy within that sample, and therefore the entropy will increase. So as we increase temperature, we will increase the entropy. When we get to phase changes, we increase the freedom of motion of the molecules, and that will also increase the entropy. So we'll get some pretty significant increases in entropy when we have a phase change. And so as we go from one phase, we go to solid to liquid, increase in entropy, and when we go from liquid to gas, we get a huge increase in the entropy. All right. So now we want to think about this graph in terms of, all right, well, what is it at standard conditions? And standard conditions is something that we call where the temperature is at 25 degrees Celsius, or in other words, 298 Kelvin, and anything that is in a gas is at 1 atmosphere, and anything that is in solution is 1 molar. But for temperature purposes, it's 25 degrees Celsius. If this was water, we'd be somewhere right about here, and that would be standard conditions. Well, the entropy that something has, because it is above absolute zero, so again, we're going to look at water liquid, so 69.9 water liquid. Well, that is the entropy that water has because it is at 25 degrees Celsius. So it's all this entropy it has because it is above absolute zero. So the entropy that 1 mole of a substance has because it is in a particular state at standard conditions, and again, standard conditions are if it's a gas at 1 atmosphere, if it's in solution at 1 molar, and then always the temperature is at 298. That is standard conditions. We have these values in Appendix C, and I will pull up Appendix C here in just a moment, but I'm going to just show you a small sampling of these right here. Generally speaking, we'll find if we compare the same substance in the gas phase versus the liquid phase, or the liquid phase versus the solid phase, that the gas phase is going to have greater entropy than the liquid, which will have greater entropy than the solids. Now, not all solids have lower entropy than all liquids, and we'll see that when we look at the numbers. But if it's the same substance, then the entropy for the liquid will be greater than the solid, and the entropy for the gas will be greater than the entropy for the liquid. We will find that standard. Oh, and just to point this out, so here if we look at H2O gas, 188.8, and H2O liquid, 69.9. So the entropy of the gas is going to be greater than the entropy of the liquid. We'll find that entropies increase with increasing size. So the entropy of these larger substances are greater than the entropies of the smaller substances. So again, hydrogen is quite small, has a smaller entropy. Nitrogen's bigger. Oxygen's bigger than that. We'll also find as we increase the number of atoms and therefore the number of bonds, then that will increase the entropy, the standard molar entropy. And we can look at this in terms of these molecules. We'll see methane is quite small, has an entropy 186.3. There's only 4 bonds in there, so there's not many ways to distribute energy in that molecule. For ethane, there are a few more possibilities because we have more bonds. There's more ways to bend and stretch and twist, and so it will have a higher entropy. Propane, even bigger, also has more bonds, so it'll have a higher entropy as well. So the bigger molecules are, and the more complex those molecules, the higher their entropies will be. So learning based on this new way of looking at things, we're going to do numbers 38, 39, and 43. Before we do that, I am going to pull up Appendix C. So here is Appendix C, and I was looking at this earlier, which is why it's down here. But it's thermodynamic quantities. I'm going to go all the way to the top here. So thermodynamic quantities for selected substances. And so the entropy let's see. So the first quantity is enthalpy. We've talked about enthalpy before in Chapter 5. We're going to be using enthalpy again. These are enthalpies of formation. We will talk about a little later in this chapter the Gibbs free energy of formation. And then this final quantity is the standard molar entropy. And that's the number that we are interested in. These are the entropies that these substances have because they are not at absolute zero. And because they are at 25 degrees Celsius, if they're a gas, they're at 1 atmosphere. And if they are in solution, it is 1 molar. So there are those substances. We will be using this extensively as we move through this chapter. So now let's go ahead and go to our in-class assignment here. And rearrange here so I can write more comfortably. All right, so for each of the following pairs, we want to indicate which substance possesses the larger standard entropy and explain. So first we'll look at 1 mole of P4 gas, 300 degrees Celsius, 0.01 atmospheres, versus 1 mole of AS4 gas, 300 degrees Celsius, and 0.01 atmospheres. Well, when we look at that, so PS4 gas versus AS4 gas, these are at the same temperature, same partial pressure. That means that really we just need to look at the difference. And I'm going to pull up my periodic table here. Here's phosphorus and there's arsenic. Since arsenic is bigger than phosphorus, arsenic is going to have the greater entropy. So the arsenic will have the greater entropy. So AS4 is larger than P4. And that is our rationale. Next, we want to look at 1 mole H2O gas, 100 degrees Celsius, 1 atmosphere. 1 mole H2O liquid, 100 degrees Celsius, and 1 atmosphere. So the key here is the phase difference. They're both at 100 degrees Celsius, but the gas is going to have a greater entropy. And and that's simply because it's a gas. Gases will definitely have greater entropy than their corresponding liquid. For the next one, this one's kind of interesting. So here we've got 0.5 moles of N2 gas, 298, 20 liters. 0.5 moles CH4 gas, 298, 20 liters. Well, with that, we need to think about this. What is the entropy going to be for these? Let's see. For this one, so N2, let's look at the size. So N2 nitrogen nitrogen has a molar mass or atomic mass of 14. So N2 has a molar mass of 28. CH4 has a molar mass of, 12 for the carbon and 1 for each hydrogen. So that's 16. So this is 28 versus 16. However, this molecule, CH4, has more bonds, as we saw on that previous thing. There's only one bond. I mean, there's a triple bond, but it's only one, one pair of atoms there. So there's only one bond there. This one has 4 different bonds. So that means there's more ways to store the energy, but it's also smaller. So the answer to this is, I don't know unless I look it up. So we're going to look up the entropy. We're going to look up the standard molar entropy at 298 for 1 mole. The pressures are going to be a little bit different on this, but that's okay. They're the same as each other. So we should be able to do a direct comparison. So I am going to go back to our entropy table here, and I'm going to scroll down and find CH4. So there's CH4, 186.3 for CH4. I'm going to write that down. So 186.3, and that's joules per mole Kelvin. And then for the nitrogen, I'm going to go down a little bit here. Didn't mean to do that. Find nitrogen in. There's nitrogen. N2, 191.5. So 191.50, and that's also in joules per mole Kelvin. So we'll definitely see that the nitrogen has a greater entropy than the CH4. So we'll say N2 gas greater entropy than the CH4 gas. And I suppose we could say that here the size was a bigger factor than the number of bonds, but I'm going to say the reason is because we looked it up. Okay. We have conflicting trends, and when there's doubt, if you have conflicting trends, you just go look it up in the table. All right, and because we looked it up is always a valid answer. So next, let's look at 100 grams sodium sulfate solid 30 degrees Celsius. 100 grams sodium sulfate aqueous 30 degrees Celsius. So that aqueous is going to have the greater entropy because it is dissolved in solution. So Na2SO4 is dissolved in H2O. And anytime you dissolve one thing in another, the molecules spread out, or the ions in this case will spread out. They will disperse, so they will have a greater entropy. On number 39, we're going to be looking at predicting whether the entropy is going to increase or decrease in each of these reactions. Really, all we need to do is to look at the number of moles of gas. If the number of moles of gas increases, the entropy will increase. If the number of moles of gas decreases, then the entropy will decrease. So when we look at this first one, 2SO2 plus O2 gives us 2SO3. That means that we've got 3 moles of gas on the left, 2 moles of gas on the right. So since we're going from 3 down to 2, we're going to say that the entropy decreases. In other words, delta S is going to be less than 0. On part B, we have barium sulfate solid goes to barium oxide solid plus H2O gas. Well, here we've got 0 moles of gas going to 1 mole of gas. So we're going to predict that delta S is going to be greater than 0. The entropy should increase because we're increasing the number of moles of gas. Here we've got CO gas plus 2H2 gas gives us CH3OH liquid. Well, here we've got 3 moles of gas going to 0 moles of gas. Delta S for this reaction should be quite negative. So if we were to calculate the delta S value for that, it would be a negative number. And then here we've got FeCl2 solid plus H2 gas gives us Fe solid plus 2HCl gas. Well, the number of moles of gas on the left is 1, and the number of moles of gas on the right is 2. Since that is increasing the number of moles of gas, we will find that delta S is also increasing. So it is positive. All right, so that's number 39. Let's do number 43. That will wrap this up. This particular set of problems, that will wrap that up. So let's do this. So use Appendix C to compare the standard entropies at 25 degrees for the following pairs. In each case, explain. Well, why don't we predict ahead of time what the entropy is going to be? Which one will have the greater entropy? Scandium gas versus scandium solid versus scandium gas. Well, we would definitely predict it's going to be the gas. So I'm going to put a little check mark there to indicate that we're predicting the gas. We'll go look those numbers up here, and well, let's go ahead and look those numbers up. So I'm going to go over to here. And we'll scroll down. Oh, there's scandium right there. So the entropy of scandium gas, let's see. I'm sorry, solid is 34.6. And for the gas, it is 174.7. 174.7. And both of those are in joules per mole Kelvin. So when we come back and look at this, the gas had a greater entropy than the gas. The entropy of a gas is going to be greater than the entropy of a solid. So that's the explanation. So next, here we've got ammonia gas versus ammonia AQ. Again, we're going to predict the gas. Let's go look up the actual values though. And nitrogen NH3. So NH3 gas is 192.5 and the NH3AQ is 111.3, and that is in joules per mole Kelvin. All right. So now when we come back and look at this, we will see, let's see, where are we? We will see that the entropy of the gas was greater again. So entropy of a gas is going to be greater than the entropy of something that's in solution, either liquid or AQ here, because it was in solution. So next we've got 1 mole P4 gas and 2 moles of P2 gas. We're going to predict the 2 moles of P2 gas because it has more molecules. This one's more complex, but this one has more molecules. So to do this, we're going to have to do a little bit of extra math. Rather than just looking up the quantities, we'll have to do just a tiny bit of extra math. So I'm going to go up here. Dang it. So there is phosphorus. So let me write down for P4, it is 280. And for P2, it is 218.1. And that is in joules per mole Kelvin. And we're now going to go back to the in-class assignment. And so for this, we'll do 1 mole times 280 joules per mole Kelvin. And no calculator needed there, 280 joules per Kelvin. Whereas for this side, we'll have 2 moles times 218.1 joules per mole Kelvin. And that's going to give us 2 times that number, which comes out to 436.2 joules per Kelvin. I trust you guys could punch that in your calculator and get that quantity if you wanted to, but 436.2 joules per Kelvin. And again, the reason this one has the greater entropy is that there are more particles. Finally, we've got carbon graphite versus carbon diamond. For this one, as far as making a prediction, we're going to go back to a picture that I showed you guys all the way back in chapter 12. And in chapter 12, we talked about different kinds of solids. And so here is the picture that I showed you back in chapter 12. Diamond is diamond. If you have a diamond, it's 1 molecule. These are sp3 hybridized, so we've got a very rigid structure. There's really not much that these can do to move around. For graphite, on the other hand, it's slippery, and that's because these individual sheets of graphite can slide past each other. And so we'll find that for graphite, there's more freedom of motion. So we would predict that the entropy for graphite would be greater than the entropy for diamond. Well, let's look at our appendix here. So here is our appendix. We're going to go up to carbon. And there are two quantities. You will notice that they are very small. Even the graphite is very small. But relative to each other, the graphite has a much higher number. So 5.69 versus 2.43. And then it's joules per mole Kelvin. And we'll go back to our picture here. So when we look at that, the graphite has a much higher entropy than the diamond. They're both very small numbers, but that graphite has a much higher entropy, and that's because there's more freedom of motion. So the graphite has more freedom of motion. And when I say that, it's the molecules of the graphite that have more freedom of motion. So now we want to go back to our presentation and look at entropy changes in chemical reactions. So we will look at entropy changes in chemical reactions. We will find we can calculate the entropy change in a chemical reaction by looking at the standard molar entropies for the reactants and subtracting those from the standard molar entropies for the products. Now, you have seen an equation like this before back in General Chemistry 1 when we did the calculation for the change in enthalpy by looking at enthalpies of formation. So here, this is pretty much the same thing. We're going to do exactly this kind of calculation. So the best way to demonstrate this is just to look at the problems. So we're going to look at number 47. And here, first thing is predict the sign of delta H or delta S for each of the following reactions, then calculate delta S. So here we've got Fe or 2 Fe2O3 solid gives us 4 Fe solid plus 3 O2 gas. Well, we've got 0 moles of gas on the left and 3 moles of gas on the right. So we would predict, our prediction here is that entropy change is going to be greater than 0. And we can be quite certain that that will be true. On this one, we've got HNO3 gas plus NH3 gas is in equilibrium with NH4NO3 solid. Since we have 2 moles of gas on the left, no moles of gas on the right, we're going to predict that the entropy change in this system is going to be negative. It would be less than 0. So we're going to go back and look at Appendix C. And I'm going to write down these quantities. So let me do iron here since it's right here. So iron, Fe solid, 27.15. I'm just going to write down these numbers. So 27.15. And then Fe2O3 is right there. Fe2O3, 89.96. So 89.96. And then O2 is right there, 205.0. And those are the standard molar entropies, and these are all in joules per mole Kelvin. So now I'm going to go back and show you the in-class assignment. And you'll see that I've just written the numbers directly beneath, and now we just want to do the calculation. So delta S is going to be equal to products minus reactants. So we'll do 4 moles times 27.15. All right, so 4 times 27.15 plus 3 times 205.0. And we'll subtract away 2 times 89.96. When we're doing this, again, always write products minus reactants, and that will give you the correct answer. Trying to figure out where. There, I put my calculator. So I do like to do the calculations on the camera so you guys can see exactly what I calculate. Also, you can see if I make a mistake, because occasionally I make mistakes. All right, so we'll do 4 times 27.15 plus 3 times 205. And then I'm going to hit enter, and that is the sum of all of those. Okay, and then we're going to subtract 2 times 89.96. And that's going to give us a value of 543.68 joules per Kelvin. Now we need to look here, hundredths place, tenths place, hundredths place. So we're going to round that to the tenths place. So I'm going to round that to 543.7 joules per Kelvin. So 543.7 joules per Kelvin. And that's definitely a positive quantity, which we predicted. We definitely predicted that. On this one, we predicted a negative quantity for delta S. We need to look up the values for these. And I've got this thing right in front of me. So I'm going to switch back over so you guys can see where I'm getting these quantities. So for HNO3 gas, it is right here at 266.4. So 266.4. All right, I made a mistake writing it down. So 266.4. And then for NH3, let's scroll down here a little bit. NH3 gas, 192.5. So 192.5. And then NH4NO3 solid, 151. And those are all joules per mole Kelvin. Let's go back and do the calculations. So here we've got, we're going to do, again, products minus reactants. So delta S is going to be products minus reactants. So 1 times 151 minus 1 times 266.4 plus 1 times 192.5. All right, so products minus reactants, punch those numbers in. So 151 minus, and I'll need to put this part in parentheses, 266.4 plus 192.5, close parentheses, and we're going to get negative 307.9 joules per Kelvin. So the moles go away when we multiply by these numbers. And this goes to the ones place, this goes to the tenths place. So we're going to round that to the ones place. I'm going to round that, and we'll just call it negative 308 joules per Kelvin. And as we predicted, the value of delta S is negative. So the value of delta S is negative. Okay, well we're at 49 minutes on this, so this is a good place. This is a good place to take a break before our next video. And just to kind of give you a heads up what our next video is, we're going to be looking at entropy changes in the surroundings.